Our closest galactic neighbor is a cosmic hall of mirrors. The Large Magellanic Cloud appears as a gentle smudge of light in the southern sky, a satellite galaxy to our own Milky Way. But this is no quiet suburb of stars. It is a turbulent laboratory where the laws of physics are stretched to their breaking point. By the end of this exploration, you will see this familiar cloud as a gallery of the universe's deepest enigmas. We are about to journey through 25 of its most bizarre phenomena, from stellar monsters that defy existence to the ghosts of explosions with no corpse. What forgotten story does a perfectly spherical blast tell us, and why are there stars that simply vanish from sight? The mysteries waiting there challenge everything we think we know about how galaxies live and die. What do you believe is the most profound secret a galaxy can keep? At the heart of this galactic mystery lies a cosmic beast of truly staggering scale. The first and most famous phenomenon is the Tarantula Nebula, known to astronomers as 30 Doradus. This is not just a cloud of gas. It is the single largest and most violently active stellar nursery in our entire galactic neighborhood, a region so immense that if it were placed at the same distance as the Orion Nebula in our own Milky Way, it would cast shadows on Earth and be visible even during the day. Its filaments of glowing gas and dust, resembling the legs of a giant spider, span over 1,000 light years, a tapestry woven by the ferocious winds and radiation of newborn stars. But the true heart of the mystery lies deep within its glowing core. There, nestled in the nebula's center, is the star cluster R136. This is a celestial gladiator arena, a packed city of stellar titans. Within it, astronomers have identified stars so monstrously massive they push the very limits of what physics says is possible. We are talking about behemoths with masses over 250 times that of our own sun, burning with a ferocious blue-white intensity so powerful that a single one outshines millions of suns. Their existence is the core puzzle. According to some of our best models, stars this huge should tear themselves apart during their own violent birth. They should not be able to hold themselves together, and yet here they are, not in isolation, but crowded together in this dense cluster. How did such extreme objects form so close to one another? It defies the quiet, gradual picture of star formation we often imagine. One leading theory suggests a frantic, chaotic process where massive clouds of gas collapse in a runaway frenzy, feeding these stellar embryos at an unbelievable rate before they can even begin to stabilize. Another whispers of stellar collisions in the crowded nursery, where large stars merge to create even larger ones. Every new image, from the Hubble Space Telescope's detailed portraits to the James Webb Space Telescope's infrared gaze that pierces the dust, reveals more of this chaotic beauty, but deepens the fundamental question. We are looking at a factory operating at maximum unnatural output, building stellar giants on an assembly line we do not fully understand. What other rules of cosmic construction are being broken in that luminous web? Within that dense cluster of giants, one star stands alone as the ultimate challenge to our textbooks. Its catalog number is R136a1, and it holds the title of the most massive star ever directly measured. To grasp its scale, picture our own sun. Now imagine stacking 250 of them together into a single, seething sphere of plasma. That is the sheer bulk of R136a1. Its brilliance is even more difficult to comprehend, shining with the power of nearly 9 million suns. For decades, astrophysicists worked with a firm rule. They believed there was a cosmic speed limit for star formation, a theoretical ceiling around 150 solar masses. The physics seemed clear. The intense radiation pressure from a newborn star that massive should blow away the very gas cloud feeding it, halting its growth. R136a1 did not just nudge past this limit, it shattered it, forcing a complete rewrite of the models. Its existence is a direct question carved in fire. How did it gather so much material so quickly? Did it form from a uniquely dense and turbulent pocket of the nebula, a perfect storm of cosmic ingredients? Or is it the product of a violent merger where two massive stars in the crowded cluster danced too close and became one? Every observation deepens the puzzle, making it a living laboratory for the most extreme stellar physics. And a star of this magnitude lives fast and dies young. Its fate is sealed in spectacular violence. In perhaps only 1 million years, a blink in cosmic time, it will exhaust its nuclear fuel. The core will collapse, possibly triggering a hypernova, an explosion orders of magnitude more energetic than a typical supernova. Some theories suggest it might skip the explosion entirely. Its core could be so heavy that nothing, not even the outgoing blast wave, can stop it, and it would implode directly into a black hole without a visible supernova at all. Either event would be a celestial spectacle. From our safe distance of 160,000 light-years, we would witness a new point of light in the Large Magellanic Cloud, outshining entire galaxies for a few weeks. It would be a final, brilliant flash from a star that defied the rules from its very first breath, a reminder that the universe often saves its most dramatic statements for the places we least expect. But the death of a star is not always the end of the story, and sometimes the aftermath is stranger than the explosion itself. Just over 3 decades ago, in February of 1987, a star in the Large Magellanic Cloud did die. It was a blue supergiant named Sanduleak -69°202, and its final cataclysm was witnessed from Earth as Supernova 1987A. For astronomers, it was a once-in-a-lifetime event, the closest supernova observed since the invention of the telescope. Its light reached our planet, a brilliant new pinprick in the familiar cloud, and it was studied with every instrument available. The data from that explosion revolutionized our understanding of how massive stars end their lives. Yet today, the central mystery of that event remains stubbornly unsolved. When the outer layers of that star were blasted into space, creating the beautiful, expanding rings of gas we see in iconic Hubble images, its core should have collapsed into an ultra-dense remnant. According to all our models, that collapsing core must have become either a rapidly spinning neutron star, a pulsar, or a black hole. But after decades of searching with the most powerful telescopes on Earth and in space, peering into the heart of that beautiful wreckage, astronomers have found nothing. No steady pulse of radio waves, no telltale X-ray beacon from a hot neutron star, no clear sign of a black hole's feeding disk. It is a cosmic crime scene with a missing body. So, where is the corpse? Several intriguing possibilities haunt this ghostly remnant. One is that a pulsar does exist, but its lighthouse-like beam of radiation is pointed away from us, making it invisible to our telescopes. Another, more dramatic idea is that the core was so massive, it collapsed directly into a black hole without the usual fanfare. A silent birth in the chaos. There is even a suggestion that the remnant could be a strange, exotic object called a quark star, a state of matter so dense it defies ordinary physics. Every new observation of that shimmering ring of debris is a search for answers. The James Webb Space Telescope recently turned its infrared eye toward the remnant, looking for any faint glow from cooling dust that might be heated by a hidden, hot neutron star. So far, the silence persists. This absence is a powerful reminder that even our best theories are maps, and the universe is the territory. We watched a star die. We charted the brilliant funeral, but the fate of its heart remains one of the most profound puzzles in modern astronomy. A ghost story written in light and expanding gas. The ghost of a supernova is not the only invisible giant hiding in this galaxy. Another, even more voracious presence was discovered decades earlier, a landmark find that changed our perception of the cosmos. This is LMC X-3, one of the very first strong candidates for a stellar mass black hole ever identified. It is a binary system, a cosmic dance of death between two objects. A normal, hot blue star orbits an unseen companion so massive and so dense that it can only be one thing: a black hole. Here, the strangeness is not in its silence, but in its relentless, hungry voice. While many black hole systems flicker on and off, going through quiet periods, LMC X-3 is a persistent, roaring source of X-rays. It is always feeding, always active, as a torrent of gas is ripped from the surface of the companion star. This stolen material does not fall directly into the abyss. Instead, it spirals inward, forming a superheated, whirling disk around the black hole called an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to glow fiercely in high-energy X-ray light, a brilliant beacon of destruction we can detect across the vast gulf of space. Yet for all its fame and constant activity, LMC X-3 guards its secrets closely. The central mystery revolves around its precise mass. Measurements suggest the black hole is likely between 5 and 10 times the mass of our Sun, but pinning down the exact number is tricky. This is crucial because that mass determines the very nature of the space-time vortex we are observing. Furthermore, the accretion disk itself behaves in puzzling ways. Its X-ray output varies in rhythms and patterns that are not yet fully understood, flickering and flaring as the turbulent flow of material churns. Is the disk stable, or is it prone to sudden, violent eruptions? What magnetic processes are at work within that maelstrom? Each fluctuation is a data point, a clue. This makes LMC X-3 more than just a distant curiosity. It is a real-time laboratory for studying the most extreme physics imaginable. We are watching the final moments of matter as it approaches the point of no return, a front-row seat to processes governed by gravity in its most overpowering form. What can this perpetual, hungry glow teach us about the final fate of all that falls into the dark? While black holes consume matter in place, other cosmic objects are flung across the galaxy at impossible speeds. HD 268835 is not just a star. It is a celestial cannonball, a massive blue giant hurtling through the sparse gas between stars at a velocity that defies simple explanation. This star is a runaway, traveling so fast it will eventually escape the gravitational pull of the Large Magellanic Cloud entirely. Destined for the lonely void of intergalactic space, its path is not a gentle drift. It is a violent, linear trajectory, a clue written in its motion that points back to a catastrophic origin. Imagine the force required to launch an object over 20 times the mass of our Sun, an object of immense gravitational pull itself, like kicking a bowling ball so hard it flies out of the stadium and into the city. This star did not achieve this speed under its own power. It was thrown. The leading theory is a gravitational slingshot of unimaginable violence. One scenario involves a binary star system where two massive stars orbited one another. If one of them went supernova, the sudden asymmetric explosion could have acted like a cosmic catapult, instantly releasing the surviving companion and flinging it away at hundreds of kilometers per second. The other possibility is a close gravitational encounter in a dense star cluster, a stellar game of billiards where our star passed too near an even more massive object, receiving a tremendous kick that sent it careening into the void. The enduring mystery is the crime scene. We have the speeding bullet, but we lack the exact location of the gun. Astronomers have traced the star's path backward, but it leads to a region of the galaxy with no obvious recent supernova remnant or dense cluster at the precise point of origin. It is as if the star has been traveling for millions of years, and the traces of its violent birth have since faded or drifted apart. As it plows through the thin interstellar medium, its fierce stellar wind collides with the gas, creating a faint, glowing bow shock ahead of it, like the wave at the prow of a speeding ship. This visible ripple is the only immediate sign of its incredible journey, a temporary wake in the cosmic sea. Where did this massive traveler truly come from, and what exact moment of cosmic chaos gave it the final, unforgiving push toward exile? That runaway star is a solitary projectile, but the galaxy also creates destruction on a truly architectural scale. Among the most spectacular structures are superbubbles, and one of the grandest is DEM L50. Picture a cavity in space so immense it could swallow our entire solar system thousands of times over, a spherical void carved not by a single event, but by generations of stellar violence. This is the essence of a superbubble. They are created over millions of years by the combined force of stellar winds from massive young stars and the sequential explosions of supernovae. These titanic events act like cosmic blowtorches, pushing the surrounding gas and dust outward, sweeping it into a dense, glowing shell that outlines a sphere of near emptiness. DEM L50 is a textbook example, yet it holds a textbook-defying puzzle. Its observed shape and the total energy radiating from its shell are slightly off. According to our best models of how these structures form, the shell should be brighter or the cavity shaped differently, given the estimated power of the stellar winds and supernovae that built it. The numbers do not quite add up. This discrepancy points to a more dramatic history. One compelling theory suggests that the bubble was not sculpted by a series of ordinary supernovae, but was instead kick-started or dramatically enlarged by a single catastrophic hypernova. A hypernova is the ultimate stellar explosion linked to the collapse of a rapidly spinning, extremely massive star like R136a1 could become. Its energy output would dwarf a typical supernova, delivering a shockwave of raw power capable of blowing a hole in the interstellar medium far more efficiently. Another idea is that an unusually dense cluster of massive stars lived and died in rapid succession right at the bubble's heart, concentrating their fury in one spot like a sustained artillery barrage. Studying DEM L50 is not just about solving a local mystery. It is crucial for understanding the grand cycle of galactic ecology. These superbubbles are the primary engines of feedback. They channel enormous energy and enriched material from stellar deaths back into the galaxy, triggering new waves of star formation in their compressed shells while simultaneously carving out vast regions where nothing new can form. They are the galactic landscapers, and DEM L50 is a unique blueprint. By figuring out which cosmic tools carved this particular cavity, we learn the rules for how galaxies regulate their own growth, distribute the elements for planets and life, and ultimately sculpt their own majestic shapes over cosmic time. What other violent signatures are hidden in the geometry of these beautiful, empty spheres? The architects of these galactic voids are the supernovae themselves, and their wreckage tells stories of staggering violence. Two of the most iconic remnants in the Large Magellanic Cloud, N49 and N63a, sit side by side in our telescopes, yet they reveal wildly different chapters of stellar death. First, consider N49. At first glance, it is a beautiful, tangled web of glowing filaments, the expanding debris from a star that exploded roughly 5,000 years ago. But look closer, and something is off. Its shape is not a serene, symmetrical bubble. It is lopsided, twisted, as if the explosion itself was profoundly uneven. This asymmetry is the first clue that something extraordinary happened here. The second clue came with the discovery of a strange, faint object near its center, catalogued as SGR 0525-66. This is a magnetar, a neutron star with a magnetic field so powerful it is a quadrillion times stronger than Earth's. Magnetars are the universe's ultimate magnets, and their formation is a matter of intense debate. Did the original star have an unusually strong magnetic field that was simply concentrated when the core collapsed? Or was the explosion itself so violently asymmetric that it spun the newborn neutron star up to incredible speeds, dynamoing a monstrous magnetic field into existence? The lopsided remnant seems to whisper support for the latter, a chaotic birth for a truly exotic object. Just a short cosmic distance away lies its neighbor, N63A. This remnant tells a completely different story, one of brutal interaction. The star that created it died in a region rich with dense interstellar clouds. When the supernova blast wave slammed into these cold, gaseous structures, it did not simply sweep them aside, it sculpted them. Chandra X-ray Observatory. Images reveal a landscape of pure celestial chaos. The shock wave, visible as a brilliant blue rim of multi-million-degree gas, plows into the clouds, crushing and heating them. Denser knots of material resist, creating dark, shadowy pillars amidst the glow, while elsewhere, the compressed gas may be triggering the collapse into a new generation of stars. Here, death literally builds. The contrast between these two neighbors is stark. N49 is the portrait of a bizarre, lopsided explosion that left a magnetic monster in its wake. N63A is the epic of an explosion meeting the landscape, a destructive force becoming a creative one. Together, they show us that no two stellar deaths are ever alike. The final act of a star is shaped by its life, its environment, and physics pushed to the extreme, leaving behind not just wreckage, but a fingerprint unique to its catastrophic end. But the story of that supernova did not end when its light first faded from view. A decade after the initial flash, something impossible began to happen. Astronomers monitoring the expanding debris ring of supernova 1987A noticed new rings of light appearing around it, rings that were not made of physical debris but of pure illumination. These were light echoes, one of the most ethereal and informative after effects in all of astronomy. Here is how this cosmic magic works. When the supernova first detonated, its brilliant flash of light radiated outward in all directions, like a sudden, omnidirectional camera flash in the dark. Most of that light came straight to our telescopes in 1987, but some of it traveled at a slight angle, striking vast, unseen sheets of interstellar dust floating light years away from the explosion. That light bounced off the dust, just like a flashlight beam reflecting off a wall in a dark room, and began a longer, indirect journey to Earth. Because it traveled a longer path, it arrived years later, creating the illusion of new, expanding rings of light that seemed to emerge from nowhere. It was the supernova's past brilliance, returning as a ghostly replay. These echoes are far more than just a beautiful curiosity. They act as a form of cosmic sonar. By meticulously tracking the precise timing and shape of each echoing ring as it grew, astronomers could perform a kind of three-dimensional tomography. They mapped the precise locations, distances, and orientations of otherwise completely invisible dust clouds that litter the space between us and the supernova. It revealed a hidden architecture of the interstellar medium in that region, showing that the space around the dead star was not empty, but structured with vast, thin sheets and complex filaments. Furthermore, by analyzing the spectrum of the echoed light, scientists could study the initial flash from angles we never directly saw. It was like having multiple cameras placed around the explosion after the fact, allowing for a more complete reconstruction of the event itself. This strange and beautiful phenomenon turned a single moment of cosmic death into a tool for exploration that lasted for decades, illuminating the dark corners of its galactic neighborhood long after the star itself was gone. What other secrets might still be traveling toward us, delayed reflections of ancient violence waiting to be read in the sky? That ghostly light revealed hidden dust, but another remnant hides its violence behind a mask of perfect geometry. Amidst the twisted wreckage of other supernovae, SNR 0509-67.5 stands apart. Captured in a breathtaking Hubble image, it resembles a celestial soap bubble or a string of luminous pearls floating in the black. Its shell is astonishingly spherical, a delicate, almost fragile-looking ring of gas expanding with serene symmetry. This perfection is the core of its mystery. In a universe governed by chaos, such order is profoundly strange. Most supernova remnants, like the lopsided N49, are messy and asymmetrical. The explosions that create them are inherently violent and often uneven, shaped by the turbulent interior of the dying star or by the clumpy environment into which they explode. So how did this one achieve such a flawless form? Astronomers are drawn to two compelling possibilities. The first theory looks inward at the explosion itself. It suggests this was a Type 1 supernova, the thermonuclear detonation of a white dwarf star pushed over its mass limit. In some models, these explosions can propagate with a remarkable uniformity, like a flame front igniting a sphere of fuel all at once, leading to a perfectly spherical blast wave. The second theory looks outward at the star's surroundings. Perhaps the explosion was not perfectly symmetric, but it occurred in a region of space that was. If the white dwarf died in a cavity of interstellar medium that was almost perfectly uniform, a void of remarkably even density, then the expanding shock wave would have encountered no resistance in any direction. It would have pushed outward equally in all directions, smoothing itself into this impeccable sphere over centuries. This remnant is more than a beautiful accident. It is a controlled experiment. By studying its pristine shape and the velocity of its expansion, scientists can peer back into the final milliseconds of the star's life, testing models of stellar detonations with a precision that chaotic remnants simply cannot provide. It asks us a quiet, profound question. Does this perfect sphere represent a moment of ultimate cosmic order in the act of destruction, or is it simply the signature of an extraordinary emptiness, a final breath expanding into absolute nothingness? That perfect sphere of destruction hints at a hidden population, the silent majority of stellar corpses. For every brilliant pulsar or feeding black hole we can detect, there should be countless more remnants that have faded into near invisibility. This brings us to the ghost population of isolated neutron stars. When a massive star goes supernova, its core often collapses into a city-sized ball of pure neutrons, a substance so dense a single teaspoon would weigh as much as a mountain. We know of these objects when they act as pulsars, sending out lighthouse beams of radiation, or when they are in binary systems, stealing gas and glowing with X-rays. But the vast majority are thought to be none of those things. They are the solitary, cold remnants drifting through the darkness alone. Having burned through their rotational energy and with no companion to feed from, they emit only a faint, fading warmth, the leftover heat from their cataclysmic birth millions of years ago. The Large Magellanic Cloud, with its furious history of star formation and death, should be a graveyard teeming with thousands of these dark cinders. Yet finding one is like searching for a single cooled ember in a vast dark forest. The detective work is painstaking. Astronomers scan the galaxy with X-ray telescopes, hoping to catch the faint thermal glow of a several 100,000-degree surface against the cold backdrop of space. Sometimes they look for sudden, brief flares, moments when the neutron star's immensely strong magnetic field might snap and reconnect, releasing a burst of energy like a cosmic static shock. Each potential candidate is a triumph of inference, a tiny blip of data that must be scrutinized and confirmed. Their elusive nature makes them a critical missing piece in the galactic census. How many stellar deaths actually produce these ultra-dense remnants versus black holes? What is the true population of these dark wanderers? Until we can find and count them, Our understanding of the life cycle of stars in the Large Magellanic Cloud is fundamentally incomplete. We are left with a haunting question. Is the space between those brilliant nebulae and star clusters actually filled with the cold, dark ghosts of ancient giants, silently tracing orbits we can scarcely detect? These dark wanderers represent a final, quiet state, but the galaxy also holds stars whose very heartbeat is used to map the cosmos. Cepheid variable stars are the universe's most reliable mile markers. These are aging, giant stars that pulsate with a steady, predictable rhythm, growing brighter and dimmer over days or weeks. The key discovery, made over a century ago, was that the slower the pulsation, the more intrinsically luminous the star truly is. It is a direct link between a star's observable heartbeat and its actual power output. By comparing how bright a Cepheid looks from Earth to how bright we know it should be based on its pulse, astronomers can calculate its distance with remarkable precision. This relationship built the cosmic distance ladder, allowing us to measure the scale of our own galaxy and, ultimately, the expansion of the universe itself. The Large Magellanic Cloud has long served as the critical anchor for this entire system. Because all its stars are roughly the same distance from us, studying its Cepheids provided the baseline calibration for the whole method. Yet this trusted foundation is showing cracks. Some Cepheids within the cloud are not behaving like textbook examples. They pulsate with slightly different patterns, or their light reveals chemical compositions that differ from their counterparts in the Milky Way. These are not errors, but anomalies, subtle clues written into the rhythm of these stellar metronomes. The mystery they pose is profound. If Cepheids are not perfectly standard candles from one galaxy to the next, then our entire measurement of cosmic distances, and therefore the calculated rate of the universe's expansion, could have a hidden, systematic error woven into it. What could cause such a divergence? The leading suspicion points to the environment of their birth. Stars form from the raw material of their galaxy, and the Large Magellanic Cloud has a different chemical history than the Milky Way. It is poorer in heavy elements, the metals forged in earlier generations of stars. A star born with less metal in its blood might pulsate in a subtly different way as it ages into a Cepheid. Alternatively, the very process of star formation in the cloud's turbulent, gas-rich environment might produce stars with different internal structures. Each anomalous pulse is therefore a message. It tells us that the history of a galaxy is imprinted on the physics of its stars, that a cosmic yardstick carved in one workshop may need recalibration in another. By deciphering why these particular mile markers tick differently, we are not just solving a local puzzle. We are checking the calibration of the tape measure we use to survey the entire visible universe. The cosmic yardsticks we rely on are forged in the fires of ancient star clusters, but some of these stellar cities bear the scars of a violent past. Globular clusters are among the oldest structures in the universe, dense spheres containing hundreds of thousands of stars, all bound together by gravity and orbiting a galactic core like a distant, glittering swarm. They are meant to be stable, enduring for billions of years. Yet in the Large Magellanic Cloud, we find clusters that tell a different story. Some appear misshapen, their outer layers stretched and distorted. Others are surrounded by faint, arcing rivers of stars, streams that flow away into the darkness as if the cluster is slowly dissolving. These are disrupted globular clusters, and their condition is a clue to a deeper, more violent history. The central mystery is one of origin and destruction. Were these clusters born within the cloud, only to be torn apart over eons by its gravitational tides, like a moon pulled too close to its planet? Or are we looking at something far more dramatic? The mangled remains of clusters that once belonged to other, smaller galaxies, clusters that were ripped from their homes during a galactic collision and are now being slowly digested by the Large Magellanic Cloud. The stellar streams are the critical evidence. They act as cosmic breadcrumbs, tracing the path these stars have traveled over millions of years. By mapping the speed, direction, and composition of the stars in these streams, astronomers can perform a form of galactic archaeology. They are reading a fossil record written in starlight. If the stars in the stream have a chemical fingerprint distinct from the cloud's native stars, it points to an external origin, a captured cluster from a devoured dwarf galaxy. If the chemistry matches, it suggests a more local, if still violent, tidal shredding. This detective work reveals that the serene cloud of light we see is not a peaceful island universe. Its history is written in conquest and merger. These disrupted clusters and their ghostly streams are the lingering evidence of a hierarchical universe, where galaxies grow by consuming their smaller neighbors. Each faint river of stars is a monument to a lost galaxy, a silent testimony to the fact that even the most beautiful structures in the cosmos are built, in part, from the ruins of others. The grand architecture of this galaxy holds its own peculiar rhythm of creation. Stretching across its heart is a massive, bright bar, a dense lane of stars and gas that acts as the central backbone of the Large Magellanic Cloud. From a distance, it appears as a unified structure, a rigid bridge of light. But zoom in, and the pattern breaks into a puzzling mosaic. Along this great bar, star formation is not a steady process. It is a series of sporadic, brilliant fireworks displays separated by stretches of cosmic quiet. Some regions are ablaze with the pink glow of newborn stars, while adjacent sections of the bar are dark and dormant, seemingly identical in composition, yet completely inactive. This unevenness is the central mystery. If the bar is a single structure, shaped by the same galactic forces, why does creation ignite in one pocket and not another? The answer lies in the invisible ingredients. Star formation requires a perfect, fragile storm. Cold, dense clouds of molecular gas must collapse under their own gravity, but they need a trigger. Within the bar, the distribution of this raw material is not smooth. It is clumpy, gathered into vast, dark nebulae that serve as stellar nurseries, while other areas are gas-poor deserts. But gas alone is not enough. Something must compress those clouds, nudging them over the edge into collapse. One powerful force is the bar's own rotation and internal dynamics. As the bar spins, it can funnel gas along its length, causing streams to collide. These collisions create shock waves that slam into gas clouds, compressing them violently and sparking frenzies of star birth. Another invisible sculptor is the galactic magnetic field. Lines of magnetic force, woven through the bar like cosmic threads, can channel flows of gas, restrain turbulent motions, or even provide support against collapse, effectively putting a region on pause. And we cannot forget the grandest influence of all, our own Milky Way. The gravitational tide from our much larger galaxy constantly tugs on the cloud, stretching and squeezing it during their long orbital dance. This external pressure might be the final trigger, stirring the pot of the bar's gas at precise intervals and in specific locations, lighting the fires of creation in a seemingly random pattern. The bar is not a monolithic factory. It is a complex engine where local density, internal dynamics, and external forces combine in a unique recipe for each site. The quiet stretches are not failures. They are regions waiting for the right combination of cosmic ingredients to come together, holding their potential in the dark. The steady heartbeat of Cepheids and the grand rhythm of the bar's star formation suggest a certain cosmic order, but some of the galaxy's oldest, largest stars are now staging chaotic final acts. Red supergiants are the bloated, cooling final stage of massive stars, swollen to hundreds of times their original size. They are famously unstable, pulsating gently as they burn through the last of their fuel. Yet in the Large Magellanic Cloud, astronomers have watched several of these giants do something far more dramatic. They have not just flickered, they have nearly vanished. Observations, particularly from surveys that monitor millions of stars night after night, have captured light curves of these red supergiants that show a terrifying plunge. A star that shone steadily for years can, in a matter of months, dim to a tiny fraction of its normal brightness, as if a cosmic hand had turned down a dimmer switch. The star does not explode. It simply fades, sometimes for over a year, before slowly returning to its former glow. This is not a gentle pulsation. It is a stellar crisis. The leading explanation for this great dimming is a colossal belch of dust. In the final millennia of a red supergiant's life, conditions in its extended, turbulent atmosphere can become perfect for manufacturing solid particles. Tiny grains of silicate and carbon can condense out of the cooling gas, like soot forming in smoke. Normally, this dust drifts away on the star's steady wind, but in these dimming events, the theory suggests something catastrophic happens. The star ejects an enormous, dense cloud of this freshly formed dust, not in a steady stream, but in a sudden, massive eruption. This cloud forms a shroud around the entire star, blocking its light from our view. It is a celestial veil, drawn closed by the star itself. The profound mystery is the trigger. What could cause a star of such immense scale to violently cough up a piece of its own atmosphere so late in life? One frightening possibility is that these are pre-supernova convulsions. The star's core, fusing ever heavier elements, may be experiencing violent instabilities that send powerful shock waves rippling through the outer layers. These waves could eject material in fits and starts, like a pot boiling over just before it runs dry. Another idea points to sudden changes in the star's internal circulation or magnetism, forces that could dredge up material from deeper, hotter regions and propel it outward in a concentrated shell. Each dramatic dip in the light curve is a potential warning sign, a signal that the star's internal furnace is becoming erratic. Astronomers watch these dimming red supergiants with intense focus, knowing that one of them could be the next progenitor of a supernova. The question hangs in the dusty silence. Is this great dimming a final, fitful breath before the terminal explosion, or merely a strange, late-life illness from which the star can temporarily recover? While stars themselves convulse and dim, entire clouds of raw material can also arrive from the void with astonishing speed. Drifting through intergalactic space, astronomers have detected high-velocity clouds, immense blobs of mostly hydrogen gas moving at speeds that defy the leisurely rotation of a galaxy. One such cloud, catalogued with the unassuming name HVC 306-2+230, is on a direct collision course with the Large Magellanic Cloud. It is a cosmic iceberg, a frozen reservoir of pristine gas hurtling toward a galactic shore. Its very existence poses a fundamental question of origin. Where did this fast-moving cloud come from? There are two leading and dramatically different possibilities. The first is that it is truly primordial, a leftover fragment from the formation of the local group of galaxies that has been wandering, untouched, for billions of years. This would make it a fossil of the early universe, gas that never cooled enough to collapse into stars, a pure sample of the building blocks that existed before the first stellar furnaces lit. The second theory is that it represents galactic theft. It could be the torn-away shred of a much smaller dwarf galaxy that ventured too close to the Milky Way or the Large Magellanic Cloud itself. Its stars held tight by gravity, but its loose outer gas stripped away and sent careening into the void. The chemical composition of the cloud holds the key. If its gas shows virtually no traces of heavier elements, no carbon, oxygen, or iron, it points to a primordial origin. If it shows even slight enrichment, it is likely the mangled remains of a galactic victim. But the mystery does not end with its past. Its future is written in its trajectory. This cloud is not just passing by. It is destined to plunge into the disk of the Large Magellanic Cloud. When it does, in perhaps tens of millions of years, the collision will be a spectacle of pure creation. The incoming gas will slam into the galaxy's own interstellar medium at tremendous speed. That impact will create colossal shock waves, compressing the gas in both clouds to incredible densities. These compressed regions will become the perfect nurseries, triggering a firestorm of new star formation on a scale the galaxy has not seen in eons. It will deliver a massive infusion of fresh fuel, a galactic meal that will power stellar birth for millions of years to come. So we are not just looking at a wandering cloud. We are witnessing the delivery of a future generation of stars, a shipment of cosmic potential racing toward its destination from a source we have yet to fully identify. That delivery of fresh gas will fuel future stars, but one object in the heart of the Tarantula Nebula is already consuming matter at a rate that defies all expectations. Designated as an ultraluminous-X-ray source, or ULX, this object is a point of light that radiates with the power of millions of suns, but all that energy is concentrated into a searing, high-energy scream of X-rays. It outshines any known process from a single star or a typical stellar mass black hole. Yet it is not the titanic engine of a supermassive black hole at a galaxy's core. It exists in a mysterious middle ground, a cosmic overachiever whose very nature is a heated debate among astronomers. At its heart lies a simple, profound question. What kind of engine could possibly produce such staggering power from such a relatively small volume of space? The leading theories propose three radically different answers, each with its own compelling evidence. The first possibility is the most exotic: an intermediate mass black hole. This would be a black hole weighing in at perhaps hundreds or even a few thousand times the mass of our Sun, a class of object that has been incredibly difficult to confirm. Such a beast would be the missing link between the stellar mass black holes formed from collapsing stars and the supermassive monsters that lurk in galactic centers. Its greater mass would allow it to pull in and accrete matter more steadily and powerfully than a smaller black hole, potentially explaining the intense X-ray output. Finding one here, in a star-forming region, would be a monumental discovery, suggesting a new path for how black holes can grow in the universe. The second theory sticks with a familiar actor, but places it in an unbelievable scenario. Perhaps this ULX is a stellar mass black hole, no more than 20 times the Sun's mass, but it is feeding at a rate so extreme it breaks our models. Normally, when matter falls onto a black hole too quickly, the intense radiation pressure should blow the surrounding gas away, shutting off the food supply in a process called Eddington limit. This object appears to be feasting far beyond that limit. To explain this, astronomers propose it might be swallowing material in thick, dense clumps, or its accretion disk might be warped in a way that funnels material onto the black hole with unbelievable efficiency. It is a cosmic glutton, consuming its stellar companion at a breakneck pace. The third, and perhaps most mind-bending possibility, is that this is not a black hole at all. It could be a neutron star, the ultra-dense remnant of a supernova, but one possessing a magnetic field of almost unimaginable strength. Such a magnetar, if it is in a binary system and actively feeding, could channel incoming matter onto its magnetic poles with such force that the resulting X-ray emission is amplified to ultra-luminous levels. This would make it a powerhouse of a completely different kind, where magnetism, not just gravity, is the primary engine of its brilliance. Each observation of this flickering X-ray beacon is a vote for one theory over another. Its pulsations, its spectrum, the way it varies in brightness over time, all are clues to its true identity. This single point of light in a nebula of giants forces us to confront the limits of our categories, asking us if we are seeing a new class of object entirely, or simply a familiar one operating in a mode we never thought possible. The engine of that ultra-luminous source forges elements in its violent heart, but across the entire galaxy, those vital ingredients are spread in a puzzling pattern. On a grand scale, the Large Magellanic Cloud is chemically immature. It possesses a lower abundance of heavy elements, what astronomers call metallicity, compared to our Milky Way. This makes intuitive sense. It is a smaller galaxy with a less intense history of star formation, so there have been fewer generations of stellar furnaces to cook hydrogen and helium into the heavier atoms like carbon, oxygen, and iron that are essential for planets and life. The real mystery is not in its overall poverty, but in its uneven wealth. The distribution of these metals is a chaotic patchwork. Some regions, particularly around recent, furious bursts of star formation like the Tarantula Nebula, are relatively enriched. The winds and supernovae from massive stars there have polluted their local neighborhood, seeding the gas with newly forged elements. Yet other areas, seemingly similar in age and stellar population, remain surprisingly pristine, as if the products of those stellar deaths never reached them. This chemical map tells a complex, layered story. It is a record of galactic ecology written in atomic proportions. The unevenness points to a history where star formation did not proceed smoothly like a rising tide, but in intense, localized bursts. Each burst would enrich its immediate surroundings, but the galaxy's weaker gravity and less structured spiral arms might have failed to mix this enriched material thoroughly throughout the entire system. The metals stay in pockets like spices not fully stirred into a batter. This creates a fascinating diversity of environments within a single galaxy. A star forming in an enriched pocket will be born with a richer supply of heavy elements in its constitution than a star of identical age born in a pristine region. But there is another, more dynamic possibility adding to the mix. The strange chemical map might also bear the signature of infalling gas, like the high-velocity cloud on a collision course. If pristine, metal-poor gas from intergalactic space periodically rains down on the galaxy, it could dilute the metallicity in specific regions, resetting the chemical clock and creating fresh pockets of primordial material amidst the enriched ones. This would be a galactic salad, tossed with both ancient and modern ingredients. Deciphering this chemical imbalance is more than an accounting exercise. It forces us to ask how efficiently a galaxy circulates the very elements of complexity. Does the Large Magellanic Cloud's chaotic chemistry reflect a fundamentally different, more haphazard life cycle compared to the well-mixed Milky Way? And if so, what does that mean for the potential of planets and life arising in such a dynamically uneven environment? These faint rivers of stars are more than just remnants of disrupted clusters. Wrapping around the entire galaxy like faint celestial spiderwebs, they are the stellar streams of the Large Magellanic Cloud. These are the true ghosts of ancient, devoured galaxies. Each stream is a fossilized timeline, a ribbon of stars torn from a smaller dwarf galaxy during a slow, violent merger that unfolded over billions of years. The stars within a single stream all share a common origin, moving together through space in a long, graceful arc that traces the exact path of their capture. They are the surviving witnesses to a process astronomers call galactic cannibalism, the primary way galaxies grow from small seeds into the majestic structures we see today. The central mystery here is not just their existence, but the full story they have yet to tell. Mapping these streams completely is a monumental challenge. They are incredibly faint, their light diluted across vast stretches of sky, and they are often lost in the foreground glare of the Milky Way's own stars. Modern sky surveys are only now revealing their true extent, showing that the Large Magellanic Cloud is entangled in a complex web of these stellar filaments. Each one represents a separate meal, a distinct chapter in the galaxy's history of consumption. The profound puzzle is reconstructing the sequence of these events. Which stream is the oldest? Which dwarf galaxy was the most recent victim? The chemical fingerprints of the stars in each stream hold the answers. By analyzing their light, astronomers can determine the abundance of heavy elements, which acts as a clock. A stream with very low metallicity likely came from a primitive, early universe dwarf that was consumed long ago. A slightly richer stream might point to a more recent merger. Piecing this sequence together is like assembling a cosmic family tree from scattered, fading photographs. But this detective work is crucial for reasons that reach far beyond a single galaxy's past. These streams are the key to understanding the gravitational dance of the entire local group. The gravity of the Milky Way and the repeated close encounters with the small Magellanic Cloud have all tugged and stretched the Large Magellanic Cloud over eons. Those interactions left scars in the form of these streams, warping their paths and perhaps even triggering some of the mergers in the first place. By modeling the precise shapes and motions of these stellar rivers, scientists can rewind the gravitational movie, testing our understanding of how dark matter is distributed and how these three galaxies have choreographed their motions for billions of years. Every faint stream of stars is therefore a dual record. It tells the tragic story of a small galaxy that lost its identity, and it simultaneously writes a line in the grand equation describing the invisible forces that sculpt our entire cosmic neighborhood. What other lost galaxies might we find, their only monuments these delicate trails of exiled suns? A brilliant new star appeared in the cloud in 2021, a sudden pinprick of light that wasn't there before. This was LMC Nova 2021, a classical nova, a different kind of stellar explosion entirely. Unlike the cataclysmic supernova that destroys a star, a nova is a surface detonation on a white dwarf, the dense, Earth-sized corpse of a sun-like star. In a binary system, the white dwarf's intense gravity steals hydrogen-rich gas from its companion. This gas accumulates on the white dwarf's surface, compressing and heating until it reaches a critical temperature and ignites in a runaway thermonuclear explosion. The star brightens by tens of thousands of times in hours, then slowly fades over weeks. While novae are common in our own galaxy, observing one in the Large Magellanic Cloud offers a crystal-clear laboratory. Every nova is unique, and this one held several surprises in its fading light. Spectroscopic analysis of the ejected material revealed unusual chemical fingerprints. Astronomers found stronger than expected signatures of certain elements, like neon, in the blasted-off shell. This is a crucial clue pointing directly to the nature of the white dwarf itself. A neon-rich composition suggests the white dwarf is unusually massive, composed of the ashes of heavier nuclear fusion. Such a massive white dwarf is closer to the theoretical limit, where it could eventually undergo a Type 1, a supernova, a titanic detonation that forges the iron in our blood. The nova's light curve, its pattern of brightening and fading, also showed unexpected hiccups and plateaus. These fluctuations are a window into the physics of the explosion itself, hinting at clumpiness in the ejected material or secondary shocks rippling through the expanding shell. Each detail forces a refinement of our models. By studying this one distant flash, we are learning about the final stages of stellar evolution in a binary dance. The chemical enrichment of the galaxy from smaller, more frequent blasts, and the potential precursor events to one of cosmology's most important explosions. The Large Magellanic Cloud, by providing a clean, distant stage for this event, reminds us that even the smaller stellar fireworks have profound stories to tell about the life, death, and rebirth of matter. That chemical map of the galaxy is written in starlight, but a far greater, invisible hand guides its every motion. The entire structure of the Large Magellanic Cloud, its rotation, its very existence as a coherent island of stars, is shaped by a ghost. This is the dark matter halo, an immense spherical shroud of invisible mass that envelops the visible galaxy and extends far beyond its luminous edges. We cannot see it, touch it, or photograph it, but we know it must be there. Without its immense gravitational grip, the galaxy would simply fly apart. The outer stars and gas clouds rotate far too quickly to be held by the gravity of the stars we see alone. Something unseen, making up perhaps 80 or 90% of the galaxy's total mass, provides the necessary anchor. Yet for such a dominant component, its precise nature in the Large Magellanic Cloud is a profound conundrum. Measuring this invisible halo is an exercise in cosmic detective work. Astronomers use the motions of stars and the flow of hydrogen gas as tracers. By clocking their speeds at different distances from the galactic center, they can chart the gravitational landscape, effectively weighing the galaxy. These observations give us one estimate of the dark matter's total amount and how it is distributed. But then, a second line of evidence emerges from the galaxy's grand billion-year dance with the Milky Way. The very fact that the Large Magellanic Cloud has survived its repeated close passes with our far more massive galaxy suggests its dark matter halo must be robust, acting as a protective shield that prevents the Milky Way's tides from completely tearing it apart. Sophisticated computer simulations that model this orbital history, however, sometimes tell a slightly different story. To match the cloud's current position and velocity, some models require a dark matter halo that is either more massive or less massive, or shaped differently than what the internal dynamics of its stars imply. This is not necessarily a contradiction, but a tension. It is a signal that our understanding of how dark matter behaves, especially during violent galactic interactions, is incomplete. Does dark matter in the halo get stripped away during close encounters, or does it hold firm? Does it interact with itself in ways we have not accounted for? The Large Magellanic Cloud, as a nearby satellite we can study in exquisite detail, is a unique testing ground for these questions. Its dark matter puzzle is a local chapter in the universe's greatest mystery. By weighing this ghost twice, using two different cosmic scales, and finding they do not perfectly agree, we are forced to refine our ideas about the very fabric that holds galaxies together. What does the silent tug-of-war between this galaxy and our own reveal about the invisible majority of the cosmos? This invisible scaffolding of dark matter holds the galaxy's shape, but within its visible bounds, a more tangible cycle of death and rebirth plays out on a breathtaking scale. The destructive fury that carves superbubbles like DEM L does not leave behind a sterile void. Instead, it sets the stage for the next act of creation. The dense, glowing shells of these colossal cavities are not merely tombstones. They are stellar nurseries, cosmic cradles where the shock waves of ancient violence become the midwives for new stars. This is the beautifully paradoxical process of triggered star formation. Picture the expanding wall of a superbubble, a tsunami of hot gas and energy moving at thousands of kilometers per second. When this advancing shock front slams into a pre-existing, cold cloud of molecular hydrogen lurking in the surrounding space, the impact is transformative. The immense pressure of the collision does not just push the cloud, it violently compresses it, squeezing the gas to densities far beyond what it could achieve on its own. In that moment of extreme pressure, gravity gains the upper hand. The compressed regions within the cloud become unstable, fragmenting and collapsing under their own weight. From this chaos, new stars are born. The evidence for this cycle is written in light across the Large Magellanic Cloud. Look at the rims of the most magnificent superbubbles, and you will often find them studded with brilliant young star clusters and the pinkish glow of associated nebulae. These are not random placements. They are the direct offspring of the explosion, a new generation sparked by the death rattle of the last. It is a galactic feedback loop of astonishing efficiency. The most massive stars live short lives and die in supernovae, their explosions clearing vast regions and compressing adjacent gas. That compression triggers the birth of new stars, some of which will themselves be massive and short-lived, destined to explode and continue the cycle. This process enriches the galaxy too. The supernovae seed the compressed gas with heavy elements forged in their cores, meaning each new generation of stars and any planets that might form around them begins with a richer supply of the building blocks for complexity. The superbubble is therefore more than a hole in space. It is a galactic engine for renewal, a mechanism that ensures stellar death is never an end, but a catalyst. In the glowing filaments of DEM L50 and its kin, we see the universe's most fundamental rhythm. From destruction comes creation, and from an ending, a legacy of new light. The glowing shrouds of planetary nebulae are often seen as serene final portraits, the last breath of a star made visible. SMP LMC 58 shatters that calm assumption. This particular nebula in the Large Magellanic Cloud refuses to hold still. Over months and years, its brightness fluctuates and its delicate structure seems to shift and shimmer, as if the ghost of the star is still moving within its shell. This is not a static monument. It is a time-lapse view of a stellar death throe, a real-time window into the chaotic final centuries of a star's life. All planetary nebulae are born from a similar, poignant process. A star like our own sun, having exhausted its nuclear fuel, swells into a red giant. Its outer layers become weakly bound, and they drift away into space, forming an expanding sphere of gas. The hot, exposed core left behind, now a white dwarf, floods this ejected shell with ultraviolet radiation, causing it to glow with ethereal colors for perhaps 10,000 years before fading. SMP LMC 58 follows this script, but with a dramatic, unpredictable twist. The central mystery is the source of its variability. Is the white dwarf star itself unstable? Some white dwarfs are known to pulsate, vibrating like a struck bell as they cool. These subtle pulsations could cause slight changes in the intensity of the ultraviolet radiation bathing the nebula, making the entire structure pulse in brightness in sync with its tiny, dense heart. But the changes in structure suggest something more complex. Perhaps the variability is not coming from the center, but from within the nebula itself. When the star shed its outer layers, it may not have done so in a smooth, steady flow. It could have been a series of violent convulsions, ejecting shells of material at different speeds and in different directions. Now, as these nested shells expand, they might be colliding with one another. Shock waves from these internal collisions could light up different filaments at different times, creating the illusion that the nebula's shape is evolving before our eyes. There is even a tantalizing possibility of a binary companion. If the dying star had a partner, the gravitational tug of that second star could have sculpted the outflow into a complex, spiraling pattern. As the nebula rotates, different dense knots of this spiral would swing into view, appearing to change the structure from our perspective. Each new observation of this variable nebula is like reading a single page from a rapidly turning book. We are catching the aftermath of a death that is, in cosmic terms, still happening. The changes are subtle, requiring patient monitoring over years, but they are there. This makes SMP LMC 58 more than a beautiful object. It is a crucial laboratory. By decoding its flickers and shifts, astronomers can peer into the poorly understood transition phase between a red giant and a stable white dwarf, a period of profound instability. It asks a haunting question about the very end of stellar life. Is the final sigh of a star a single, steady exhalation, or is it a fitful, gasping series of breaths echoing in its own glowing shroud for millennia? These subtle whispers of order extend beyond stellar streams to the very cities of stars themselves. Among the hundreds of star clusters scattered across the Large Magellanic Cloud, a strange, large-scale pattern emerges when you step back and look at the galaxy as a whole. The orientations of these clusters, the directions their elongated shapes point, are not completely random. There appears to be a faint tendency for them to align, a subtle suggestion of a shared directionality across vast distances. This is deeply puzzling. Star clusters are meant to be independent island universes, each forming from the collapse of its own isolated giant molecular cloud, tumbling through space with no knowledge of its neighbors. Their shapes should point every which way, like leaves scattered by the wind. The hint of alignment, therefore, is a ghostly fingerprint of some larger, organizing force that imprinted itself on the galaxy's structure long ago. So what invisible hand could possibly line up these stellar cities? Astronomers are investigating several powerful suspects. The first is the galactic magnetic field. While incredibly weak by earthly standards, these vast webs of magnetic force are woven through the entire interstellar medium. During the epoch of intense cluster formation, these field lines could have acted like cosmic guide wires, channeling the collapse of gas clouds along preferred directions, imparting a similar spin or elongation to the clusters that formed within them. The second suspect is the relentless gravitational pull of our Milky Way. As the cloud orbits our galaxy, the tidal forces, the difference in pull between the side closer to us and the side farther away, stretch and squeeze it. This tidal stretching could have preferentially shaped the giant clouds that birthed clusters, lining them up along the axis of tension, like taffy being pulled. A third possibility looks back to the galaxy's infancy. Perhaps this alignment is a fossil, a memory of the structure of the primordial gas disk from which the Large Magellanic Cloud itself coalesced. If that original disk had large-scale swirls or waves in its density, the first massive clusters to form might have inherited that preferred orientation, setting a pattern that later generations subtly followed. This is not a dramatic, glaring anomaly, but a statistical whisper in the data. Confirming it requires painstaking measurements of countless clusters and ruling out every possible observational bias. Yet, if it is real, this faint alignment is a profound clue. It tells us that the chaos of star formation is not entirely chaotic. Even the birth of these magnificent, independent stellar societies may be gently guided by the galaxy's deepest rhythms, its hidden magnetic heartbeat, its tidal dance with a giant neighbor, or the enduring echo of its own creation. What other subtle patterns are woven into this seemingly chaotic cloud of light, waiting for the right perspective to reveal them? This subtle alignment of clusters speaks to a hidden order, but the galaxy's violent history seems to be missing its most obvious monuments. Given its furious pace of star formation and its abundance of massive, short-lived stars, the Large Magellanic Cloud should be littered with the expanding wreckage of supernovae. Astronomers can calculate a predicted number based on the stellar birth rate and known lifespans. Yet when they scan the galaxy with radio and X-ray telescopes, the census comes up short. There are fewer supernova remnants than the models say there should be. This is the missing remnant problem, a quiet discrepancy with loud implications for our understanding of how galaxies live and die. So where did all the corpses go? Several possibilities haunt this absence, each pointing to a different gap in our knowledge. The first is simply that we are not seeing them. Many remnants could be too faint. After a few tens of thousands of years, a remnant's glowing shell expands and cools, its radiation fading from visible light into the radio spectrum, becoming a whisper against the background noise of the galaxy. Our surveys might be missing these elderly, diffuse ghosts. The second idea is more dramatic. Perhaps they dissipated faster than we thought. If a supernova explodes into a region of space that is particularly empty, a low-density cavity, its blast wave encounters little resistance. It can expand rapidly, thinning out so quickly that it essentially vanishes from detectability in a surprisingly short time, leaving behind no lasting monument. The third possibility challenges our identification skills. Maybe we are looking for the wrong thing. Some supernovae, particularly those from the most massive stars, might collapse directly into black holes with a whimper rather than a traditional bang, producing a faint, brief flash, but no lasting, expanding shell of debris. Others might leave behind a remnant that looks nothing like the classic ring. It could be a tangled, faint web easily mistaken for an ordinary nebula. This missing remnant problem is not just an accounting error. It forces a re-evaluation of the entire stellar life cycle in this galaxy. If remnants are disappearing quickly, it changes how we model the feedback of energy and heavy elements into the interstellar medium, the process that regulates future star formation. Are we overestimating how often massive stars actually die in supernovae? Or are we underestimating the galaxy's ability to clean up the evidence? Each missing remnant is a silent question mark over a predicted cataclysm, a reminder that the final stages of stellar evolution may hold more quiet exits than our theories have allowed for. The silent exits of those missing supernovae might leave no visible trace, but their violent energy could be escaping in another invisible form. Racing through the void at nearly the speed of light are cosmic rays, atomic nuclei stripped of their electrons and propelled to energies far beyond anything we can create in our most powerful particle colliders. For over a century, their origin has been one of astrophysics' greatest puzzles. Now, mounting evidence points a finger at our turbulent neighbor. The Large Magellanic Cloud appears to be a significant source of these mysterious, high-energy visitors. This transforms the galaxy from a visual spectacle into a hidden particle accelerator of staggering scale. The core mystery is a simple one with a profoundly complex answer. So, what cosmic engine within the cloud is capable of hurling pieces of atoms across the universe with such ferocious force? The prime suspects are the sites of its most violent events. Consider the collective fury of all those supernova remnants, both seen and unseen. Each expanding shock wave is a natural particle accelerator. As the blast front plows through the interstellar medium, it creates a turbulent, magnetized barrier. Charged particles, protons, and atomic nuclei can become trapped in this chaotic zone, bouncing back and forth across the shock wave like pinballs. With each crossing, they gain a little more speed, a little more energy, until they are finally flung free, ejected into intergalactic space as cosmic rays. In a galaxy as active as the Large Magellanic Cloud, the combined shock fronts from thousands of supernovae over millions of years could create a diffuse, galaxy-wide accelerator, constantly pumping out these energetic particles. But there is another, more concentrated suspect. The environment around the galaxy's black holes, particularly the ultraluminous-X-ray source and systems like LMC X-3, are cauldrons of extreme physics. The intense magnetic fields and relativistic jets potentially launched from these systems could act as focused cannons, accelerating particles along narrow, powerful beams. The recent detection of very high-energy gamma rays from the direction of the Tarantula Nebula is a crucial clue. Gamma rays are often the telltale sign of cosmic ray activity, produced when these speeding particles collide with slower-moving gas or light, creating a secondary flash of energy we can detect. The fact that this signal seems to emanate from the cloud's most active region suggests the accelerator is running at full power there. Studying this nearby source is a unique opportunity. Instead of trying to trace a cosmic ray's path back across millions of light years of tangled magnetic fields, we have a known active factory we can observe in detail. By correlating the gamma-ray maps with the locations of supernova remnants, star-forming regions, and black hole candidates, astronomers hope to pinpoint the exact mechanisms of acceleration. Is it a democratic process, driven by the combined shocks of many ordinary supernovae? Or is it dominated by a few extraordinary, monstrous engines? Each high-energy particle that arrives from its direction carries a faint imprint of the cloud's most violent processes, making this beautiful smudge of light a powerful beacon in the invisible sea of radiation that fills the cosmos. From the ghostly trails of ancient galaxies to the silent birth of black holes, our journey through these 25 phenomena reveals a fundamental truth. The Large Magellanic Cloud is not a static picture. It is a living, breathing, and violently creative entity. Every strange object we have encountered, from the runaway stars to the missing supernova remnants, is a piece of a larger puzzle. These are not mere curiosities. They are active experiments in extreme physics, unfolding in real time just beyond our galactic doorstep. Each mystery represents a frontier where our current understanding meets the raw, unscripted chaos of the cosmos. By studying why a star fades behind its own dust, or how a bubble grows too large, or where the cosmic rays are born, we are not just solving local riddles. We are stress-testing the universal laws that govern all galaxies, all stars, and ultimately, our own place in this vast story. This neighbor of ours, a gentle smudge to the naked eye, is in truth a roaring engine of creation and destruction. It is a teacher using its bizarre phenomena to write lessons in light, gravity, and time. So the next time you find yourself under a clear southern sky or simply gazing at an image of this celestial cloud, remember what churns within it. See the stellar nurseries forging giants, the black holes feeding in silence, and the ancient streams of stolen stars. Let your wonder be guided by knowing that every point of light holds a potential revolution in our understanding. Which of these 25 strange phenomena captured your imagination the most? Was it the missing heart of supernova 1987A, the perfect sphere of that one remnant, or the ultraluminous engine-defying classification? Share your thoughts below, and if you crave more journeys into the deepest cosmic mysteries, consider subscribing to continue exploring with us. The universe is filled with stories waiting to be told, and the next great discovery might just be hiding in the cloud you now know so much.